Our planet keeps a meticulous diary of its history. This diary is written in the language of rocks, layers upon layers of them, each telling a story of a bygone era. But what happens when a page goes missing from this grand chronicle? Scientists at Stanford University stumbled upon a perplexing gap in Earth's rock record. A 34-million-year void spanning a period known as the Eocene-Oligocene transition. This discovery, like any good mystery, has sent geologists scrambling for answers. This missing chapter coincides with a pivotal period in Earth's history. The Eocene-Oligocene transition, approximately 34 million years ago, marked a time of dramatic climate change. Temperatures plummeted, ice sheets grew, and the planet underwent a major reorganization of its ecosystems. Understanding this transition is crucial for comprehending Earth's climate system and its potential for future change. The Stanford study, published in the journal Geology, focuses on a geological formation in Italy. This formation, known as the Contessa section, is renowned among geologists for its remarkably complete record of the Eocene-Oligocene transition, or so they thought. The Eocene epoch, which began about 56 million years ago, was a time of incredible warmth. Palm trees swayed in what is now Alaska, and crocodiles roamed the Arctic. But this balmy era was not destined to last. As the Eocene gave way to the Oligocene epoch, Earth's climate underwent a dramatic transformation. The transition was triggered by a complex interplay of factors, including volcanic activity, changes in Earth's orbit, and a decrease in atmospheric carbon dioxide levels. The result was a significant drop in global temperatures, leading to the formation of the Antarctic ice sheet and a cooling of the planet's oceans. This period of rapid climate change had a profound impact on life on Earth. Many species unable to adapt to the cooler conditions went extinct. Others migrated to lower latitudes or evolved new characteristics that allowed them to survive in a changing world. The Eocene-Oligocene transition serves as a stark reminder of the Earth's capacity for dramatic climate shifts. By studying this ancient event, scientists hope to gain a better understanding of how our planet's climate system works and how it might respond to future changes. Imagine Earth's history as a giant book. Each layer of rock represents a page in this book, with the oldest layers at the bottom and the youngest at the top. These layers, known as sedimentary rocks, are formed over millions of years as sediments like sand, mud, and the remains of organisms accumulate and harden. Just like the pages of a book, sedimentary rocks preserve clues about the past. By studying the types of sediments present, the fossils they contain, and the chemical composition of the rocks, geologists can piece together a picture of what Earth was like millions of years ago. For example, the presence of fossilized coral reefs indicates a warm, shallow marine environment. Layers of coal tell us that swamps and forests once flourished in a particular region. And the chemical signature of the rocks can reveal information about past climates, ocean currents, and even volcanic eruptions. Sedimentary rocks are essential for understanding Earth's history. They provide a tangible record of past environments, life forms, and geological events, allowing us to trace the evolution of our planet over billions of years. The Stanford researchers, led by geologist Jeremy Caves-Rugenstein, were expecting to find a continuous record of sedimentation spanning the Eocene-Oligocene transition at the Contessa section. After all, this site was chosen for its reputation as a complete archive of this crucial period. However, what they discovered instead left them baffled. Using a technique called magnetostratigraphy, which analyzes the magnetic properties of rocks, the team meticulously dated the sediment layers. To their astonishment, they found a significant gap in the rock record. Approximately 34 million years worth of sediment was simply missing. It was as if several pages had been ripped out of Earth's history book. This unexpected finding sent shockwaves through the geological community. How could such a substantial chunk of time be unaccounted for, in a location known for its complete geological record? The missing layers presented a perplexing puzzle, challenging our understanding of sedimentation patterns in Earth's history during this critical period. The Great Ocean Conveyor Belt, a possible explanation. The missing sediment layers sent scientists on a quest for explanations. One theory points to the ocean circulation system, the Great Ocean Conveyor Belt. This system transports warm waters from the tropics towards the poles and colder waters from the poles towards the equator. It regulates Earth's climate by distributing heat globally. During the Eocene-Oligocene transition, a shift in ocean currents may have occurred. Changes in temperature or salinity could have altered sedimentation patterns, leading to the observed gap in the rock record. Section 6. Starvation in the deep. A new theory emerges. While the ocean current theory offers a plausible explanation, Stanford scientists propose a different hypothesis. They suggest the missing sediment layers result from deep-sea starvation. During the Eocene-Oligocene transition, as ice sheets expanded, nutrient delivery to the deep ocean reduced. This created a starvation effect, leading to a decline in marine life. Fewer organisms contributed to sediment formation. This theory highlights Earth's interconnected systems and climate change's impact. Section 7. Challenging existing models. A paradigm shift. The discovery of the missing sediment layers and the subsequent scramble for explanations have sent ripples through the field of geology. It challenges our existing models of sedimentation, particularly during periods of significant climate change. Traditionally, geologists have assumed that sedimentation rates remain relatively constant over long periods, barring major catastrophic events. The Contessa section finding, however, suggests that this assumption may not always hold true, especially during times of rapid environmental change. This discovery underscores the need for a more nuanced understanding of how sedimentary records are formed and how they reflect Earth's history. It highlights the importance of considering factors such as ocean currents, nutrient cycles, and biological productivity when interpreting geological data. The missing layers serve as a reminder that Earth's history is not always neatly preserved in the rock record. There are gaps, inconsistencies, and surprises waiting to be uncovered, each challenging our assumptions and pushing the boundaries of scientific understanding. Section 8. Echoes of the past, lessons for the present. The Eocene-Oligocene transition, with its dramatic climate shift and its impact on life on Earth, holds valuable lessons for us today. As our planet grapples with the consequences of human-induced climate change, understanding past climate transitions becomes increasingly crucial. The rapid temperature drop during the Eocene-Oligocene transition, while triggered by natural processes, serves as a stark reminder of Earth's climate sensitivity. It highlights the potential for significant and rapid climate change, even in the absence of human interference. Moreover, the extinction of numerous species during this period underscores the vulnerability of ecosystems to rapid environmental change. It serves as a cautionary tale, reminding us that our actions today have the potential to trigger profound and irreversible changes in the natural world. By studying past climate transitions such as the Eocene-Oligocene event, scientists can gain insights into the potential consequences of our current trajectory. These insights can inform our efforts to mitigate climate change, adapt to its impacts, and preserve the planet's biodiversity for future generations. Section 9. The urgency of climate action. The discovery of the missing sediment layers and the insights it provides into Earth's past climate reinforce the urgency of addressing our current climate crisis. The parallels between the Eocene-Oligocene transition and the changes we are witnessing today are too striking to ignore. Like the Eocene-Oligocene transition, we are experiencing a rapid increase in global temperatures, primarily driven by the burning of fossil fuels and deforestation. These activities release greenhouse gases into the atmosphere, trapping heat and altering Earth's climate system. The consequences of inaction are dire. We are already witnessing rising sea levels, more frequent and intense heat waves, changes in precipitation patterns, and an increase in extreme weather events. These impacts will only intensify if we fail to curb our emissions and transition to a more sustainable future. The lessons from the Eocene-Oligocene transition are clear. Earth's climate is capable of rapid and dramatic change, and these changes can have profound and lasting impacts on life on Earth. We have a responsibility to act now to mitigate climate change and protect our planet for future generations. Section 10. Unraveling Earth's Mysteries. The quest continues. The discovery of the missing sediment layers at the Contessa section is just one example of Earth's mysteries. As scientists probe our planet's depths, they uncover new insights into its history and evolution. Each discovery, whether it's a missing layer of sediment, a fossilized creature, or a new understanding of Earth's processes, deepens our appreciation for our planet. The quest to understand Earth is an ongoing journey driven by curiosity and a desire to unravel its mysteries. Section 11. Our Place in Time, a Deeper Understanding. As we delve deeper into Earth's history, we gain a profound appreciation for our place in time. We are but one species among countless others that have inhabited this planet over billions of years. The Eocene-Oligocene transition reminds us of the impermanence of any single species or ecosystem. It highlights the interconnectedness of all life on Earth. By studying Earth's past, we understand the forces shaping our present and future. We appreciate the delicate balance of Earth's systems. The quest to understand Earth's history is a journey of self-discovery. It connects us to our planet's past and inspires us to become better stewards of our future.